about it if we want to do that first.
Yeah, sure. All right, so I kicked off the recording. It's June 9th. Here to talk about resource management topics in SIG Node. Kevin or Victor, feel free to run the agenda.
Okay, I can, I'll share the screen. Oops, I guess I can't, unless you want to make me co-presenter or co-host. Derek, can you make me co-host so I can share the screen? Okay. All right, can everybody see the document?
Yes.
Oh, great. So why don't we start, we'll just go over the topology manager enhancements for 119, go or no go. Kevin, did you want to talk to one of these? I think this one, the first
sure,
one.
go ahead and open both of them,
okay.
And then we can flip back and forth. So this is the first one that I talked about a few weeks ago, this get preferred allocation extension to the device plugin API. After some back and forth and some feedback, you know, I tried to address all the feedback we had, and the final conclusion was kind of it wouldn't hurt anything to actually add this. But that said, I probably won't have time to add it into 119. So it's been merged. It's something that we will probably move forward with unless there's huge objections to it before 120 comes around. I know Alexander has some feedback that he's given a few times that he's added here. So if anyone wants to +1 that or you know, add any more feedback at all, please go ahead and do so because it probably won't be happening in the 119 timeframe anyway. So that's all I really have to say about this one. Just to let people know that we actually merged it. We decided to merge it, but it won't be making it in 119.
So Kevin, regarding this 19 part, is it because you don't have time or is it because we're already too late in the schedule for it?
Probably a combination of both. I don't know. I don't have time. I'll say that much to start with. And then the second piece, I guess, is I'm not actually sure. I think Derek would need to speak to that, whether we're even allowed to do these things at this stage, since we only now just merged this and it's technically after the enhancement freeze and all that.
I think in this case, how would I want to phrase this? Honestly, the scope of enhancements was originally for things that spanned SIGs. I think SIG Node's one of the SIGs within the community that is more structured on kind of making changes, always tracking an enhancement. From my perspective, I think this is an incremental tweak to an existing feature that I wouldn't think is as I wouldn't have objected to merging this. We might have been scolded, but I don't think it doesn't have a broad impact across components within the project that it didn't seem like a significant concern.
Yeah,
I think the only reason I would have thought maybe it wasn't okay is because it does touch the API to the external device plugins. So it's not like it's just a completely internal change to the kubelet.
No, I'm saying it's not. It doesn't really span the scope of a single SIG.
Yep. Got it.
Because why I'm asking is because, of course, the season of vacation coming, but on our hand, we might have like ISMA time and probably Christian time to actually help with that. Because we also benefit from this feature. It's like my comments were merely based on like the detail of data representation, not the whole feature.
Okay, yeah, if someone else has, excuse me, time to work on this, then I'm happy to review it. Yeah.
Okay. Any other discussion on that, Cap? Okay, let's go to the next one, which is pod level resource alignment. So is BG on the call?
Hey, it's Chris here.
Hey, Chris.
So last week Derek left us some comments and also asked to include the how the init containers will be handled and the situation with debug or ephemeral containers. So BG today applied those changes. The example here is a little bit old because we did it more in the pod scope way. To be the same as is the pod scope defined, but it is generally looks like this. And yeah, I wanted to ask for what is the decision or the opinion on that.
Yeah, so thank you for making the updates. I think it's easy to forget that we have multiple types of containers and folks may want to add new ones. That it's good that we just express the interaction of the system with all of them. For myself, I think the presentation that BG put out explaining that in a 5G deployment, I think you had a typical 5-server node setup where 2 of the nodes would be dedicated to running user plane functions. That kind of topology made sense to me, and at least made it clear that this setting would be used for at least a subset of nodes in that topology that I felt like I had a better understanding. So for myself, I have no objection to this. So assuming nobody else has any major objection, I'm happy to proceed on this.
Yep, same. I'm a +1.
Well, I wouldn't say it's major objection, but in overall, we are again trying to create the implementation which will use only one small subset of functionality. So like 5G is an important topic. Yes, we understand the problem with it, but when like there are also other scenarios like with generic workloads like databases where resource alignment might be needed. And I don't believe this proposal is fully covering all those scenarios.
Yeah, so I guess I...
Let me look for latest comments. Maybe I will write it down on the GitHub.
Is that Alex speaking?
Yes, it's me.
Yeah, okay. So Alex, the way I kind of reflected on this was, I kind of wanted to have like I'm inclined to want to have a bias to action where the use case was clear and the change was relatively incremental. I don't think that prohibits us from doing more in the future for general purpose workload scenarios. So I think I did put a comment in there that like whether we do like this whole discussion is basically a node local decision, and whether that node local decision is container or pod bounded. Anytime we go to do something that's not a node local decision but a pod level decision, like we're gonna have to figure out a policy to mitigate that. So I didn't really want to block on that. But from my perspective, we didn't yet have a one size fits all solution identified that evolving the per node policy to just be either per container or per pod felt reasonable in light of the use case that BG presented. So that was kind of where I was right now. Otherwise, I feel like we're bound to potentially make no forward progress.
Yeah, let me check the latest comments. I haven't checked it for the last few days, so I'll check your comments.
Okay. All right. So then let's, Alex, we'll let you spend today reflecting on it some, and then tomorrow we'll look to see if there was any new reflections or insights you could add, and we'll look to hopefully see your +1, and we'll proceed tomorrow afterwards.
All right. So that covers the enhancements for 119. So I think, do we want to go on and let Ismo do his presentation next? So I think the other ones are sort of later and may take a little bit more time. Is that good?
All right. So can you share the slides, or can you make me this co-host so that I can share them? It's the next link.
Yeah. So I can share, or I think Derek would have to make you co-host. Either way is fine with me.
No, it seems to be working. So if you just can
Yep.
like move forward when I ask, then it's fine. So let's.
Okay.
So this is me and Alexander. We were thinking about how to best like do this topology based resource selection like in the future. So this, I think the idea here is that this is not a small incremental change, but this is more like us reaching towards like an end goal, which would be to get this as flexible handling of topologies as possible, and also like to get an algorithm which would sort of like give us a chance to efficiently find those good sets of resources. So here's on this slide there is this link to this GEP, this overall this Git pull request, and then this direct link to this file if you want to find it. And then here are the two main goals that we sort of have. That we want to have a generic enough mechanism that we can handle these complex topologies. And what we mean is that the devices might have connections, either internal connections or like connections between devices, which the system or the topology manager itself is not aware. And then we can also like start moving out of this NUMA model, that everything is connected to NUMA nodes, and instead like think about costs between the devices themselves. And because we have this concept of connecting devices between each other and to the system devices such as the CPUs, and there are costs involved, then actually what we have is a graph. And this means that we actually can have graph algorithms to actually like find the resource sets, which is good because there's a ton of existing work on this. And if you go to the next slide, please. Then the obvious question is that if there is a cost between two resources, then what does that mean? And it's just a value. So it somehow like tells that what is this distance between two devices. So it can represent latency or it can represent bandwidth, but it somehow like tells that resources or devices which have small costs between themselves are somehow like close, and we should try to get a resource set which has as small as possible like total cost. And since these are just numbers, these are like these kind of like a bit abstract ideas, then we just like normalize them when we count costs. And even though the costs can be sort of like one directional or asymmetric, so it can be expensive to reach from this device to that one, then we just like what we do is that we just like zoom the costs between the devices both directions to get some sort of overall idea how they are connected. And next slide, please.
Oh, sorry, could I have a question?
Yes, of course.
Do you plan to set these costs only once at the beginning of the at the startup time, or you plan to update these costs online as the assignments are changing?
This is a good question. It depends on how this will actually be implemented.
Okay.
But right now we are on this prototyping stage, and so far we have been only being like considering fixed costs.
Okay.
But But it sort of depends how we actually want the cost, because the cost can come from multiple of places. Like, but for example, if the device plugins can tell costs, if it's part of the topology information that they are sending back, then it's like maybe fixed. But if it is something which we ask from the device plugin, then it can be like something which is dynamic.
So it's related to a discussion what we had about the Kevin's cap about get preferred allocations. So right now we have two means of returning information from device plugin. One is list and watch, like where the plugin is reporting the information about each instance of the device. So we can add that information there, or we can have additional call, which will say, give us updated information about what is your current state. And for system resources like memory, CPUs, and so on, that can be recalculated dynamically based on what we are getting from, I don't know, like C-Advisor, for example, or based on some other events, if we want. So,
Okay, thanks.
Assumptions here yet.
Okay, I see. Thanks for explanation.
Yeah, and on this slide is the algorithm that when we do have the costs, then this is what we plan to do with them. So on the left side, on the gray background, there's a YAML file which is sort of example that how the costs could be represented. And for example, on the very top left, there is this device which is the intel.com/fpga/fpga1, and it has the cost of 10 to CPU1, and it has the cost of 12 to this Intel.com/QAT/QAT0 device. So this is how the costs could be like described. And we have already like thought about some like performance enhancements. For example, it turns out that many devices are somehow like grouped together, so that they don't have like, even though a physical device can have like many sort of sub devices, then they just might share the common costs to everything. So we can just like treat them as one. And on the right side of the slide, there is this example graph that is generated from this. If somebody has these resource costs, which on the left side, and then do a request that request this one CPU and one FPGA device and one QAT device, and that's what's like said on the blue box in the middle. So the graph is a layered graph. So the idea is that we need to traverse through every like device type layer using the red arrows. Like for example, from CPU, we pick a CPU, and then we pick an FPGA device, and then we pick a QAT device, and then we go to the end. And the green arrows are sort of this layer internal. Yeah.
Quick question. So, if I'm reading the data in the YAML on the left, the top has the FPGA1 with a distance of 10 to CPU1.
Yeah.
But then it has CPU1-2 with a distance of 5 to FPGA1.
Yes.
Is that is the CPU1-2, is that referring to first socket, second core on the socket, or third core on the socket?
No, it's just this notation of grouping these devices. So it just refers to CPU devices 1 and 2.
So this is it's non-transitive relationship?
Yeah, so what we do is that because these connections, they can be asymmetric. And also that if we ask device plugin to sort of like approximate their costs, then they can in principle give whatever numbers which might not map to the other side of the number. So we just are counting them together. So if you look at this graph on the right side, then the link that you're talking about is coming from the CPU to FPGA1. It's on there, and it's 15. So it actually is 10 plus 5. So our best like approximation of the cost is 15 there. And the arrows on the graph, they don't mean that these are now the sort of the arrows between all the possible connections which we have set here. But we have just like built the graph in this layered format. So the idea is that we just need to go through the graph once using the red arrows, and then
but it's not a single direction graph, isn't it? It's like there are arrows from the quick assist device
yep.
back to the CPU. It's not one way, right? So it's a cyclical graph.
It shouldn't be cyclical except for this layer internal arrows. For example, this FPGA arrows, the green arrows are in a cycle, because it means that if we would have a case where we would have like several FPGA devices in the request, that somebody would request like 3 FPGA devices, then we would need to actually like travel inside the one FPGA layer in this graph to actually pick as many resources as we sort of like need before going forward to the next sort of resource layer. So the black arrows, this is now sort of implementation detail a bit, but the black arrows here, they represent this sort of these costs which are not part of the traversal, but they're part of the cost calculation. So example, there is a cost between CPUs and QAT devices, which we are representing with that black arrow, which has this 17. So it's just something which we need to sort of like take into account when we are calculating the total costs. Because the idea of the algorithm is that we are trying to find a solution which has the least or the minimal total cost.
Sure. No, I totally get that. The data that's represented in the YAML to the left, I'm assuming would be what the device plugin produces back to the device manager.
Yes, that's the next step is that we go to how to determine the costs. But so in this whole KEP, it is sort of like split into two. So the first phase is maybe that when we do have the costs between the devices, then what we do with them. And this algorithm is now an example that how we can find these good resource sets like pretty fast. So this algorithm is faster than the current topology manager algorithm that we have, but it is like probabilistic at the moment because the problem itself is NP complete. So with the current like understanding, it can't be solved like within polynomial time. But we can like get these heuristics and get these probabilistic algorithms which actually give us like good bounds on the algorithm execution time.
So practically what we are trying to optimize instead of current algorithm topology manager where we just do like iterations of bit mask shifting and trying to find the combination. Now we have actually proper algorithm which have like good mass theory behind how to traverse them.
Sure. Yeah. No, that totally makes sense. My not worry, but my concern would be about the user experience, in particular, how someone who's diagnosing or debugging a particular issue in this code might go about determining where a bug might exist. That's primarily my concern.
Yeah, that's a very
I could see
concern.
something like that too. It would almost say, hey, given this YAML file, I would almost need a tool to feed this in to say, hey, what's the resultant output, and to know if it was correct, and then to go into the system and debug.
Right.
Yeah,
I mean, I don't think that Ismo is suggesting that this YAML file would be like a static file on disk or anything. I think that's essentially what would be produced from, looking at NumaCuddle and, stuff like that, right? Or the node discovery agent.
Yeah, that's right. So the background with this is that I made this proof concept like implementation of the algorithm, and that is the file which I'm feeding. It is on the left, and then the result I did it using this Go num, which is this numerical computation, this library for Go, which actually can output the graphs, which is what you see on the right. So that is the background with this. But the idea is that the numbers themselves, they are like they are coming from various sources, and they're not on a file in the system. So this is just an example that how we can get. Go ahead.
From my perspective, as long as we have a good way of getting these numbers and we trust simulated annealing or whatever algorithm we're using to traverse the graph, I don't think it would be that difficult to debug it. I'm waiting to hear how the numbers are generated, though. That's been my feedback multiple times. So
Yeah.
we'll get there in a minute.
Yeah, let's,
I'm also very interested how you generate these numbers, because this is the fundamental. Thanks. Okay. Thanks.
okay, so let's go forward to the next slide then, which is how to determine the costs. And we were thinking that there are like possibly 4 of these kind of fundamental cases that what kind of like costs can exist in the system. And the case 1 is that the costs between system devices. And the idea is topology manager is the component which actually like takes care of finding these. And these one they can be had from this like what these are reported by the Linux kernel mostly. You can with this numa-ctl and friends, you can get access to these. So what we have on the picture is that we have like these various components in the system, components in the system. We have the memory controllers, we have the CPU cores and CPU threads and CPU sockets and so on. The numbers here, they are costs between them. So the costs themselves, they are just something which I added here for demonstration purposes. These are not like real data. But with tools like numa-ctl, then you can actually see that how the actual CPU cores are connected to each other, that what are the costs which the numa-ctl approximates there to be. So the idea is the topology manager will take care of finding out these costs. And at case 2, if we go one slide down, is the device internal costs. Like, for example, there can be like GPU devices which are tiled. And this is, I think, the case that the Kevin's KEP is solving, which is that if the device plugin knows that there is internal structure within the device, it can then try to sort of give back like device instances or the resource instances which are close to each other. And again, here the 14 and the 7s, they are just like random numbers which I added here to sort of demonstrate that there can be different costs between different items in the single device. And the only like component which actually can do this is the device plugin, because it is supposed to have sort of the domain knowledge to actually understand what is going on. And that's also how it's done in this Kevin's KEP. And then if you go to the next slide, please. And this is an interesting case. And idea here is that devices are connected within this PCI bridge topology. So the 3 dots on the top, they just sort of like refer to the rest of the system that at some point that will be connected to the CPU cores. But here, for example, you can see that it would make sense to actually like have devices bar 0 and foo 0 go together, and device bar 1 and foo 1 to go together. And this case, actually, we are planning to solve with a helper library. So we can get the topology for a device which is connected to this PCI bridge. And then we can use the library to find the costs or the distances to other devices which are connected to the same PCI bus.
Can I ask a quick question here?
Sure.
How is this different than case 1? I know case 1 was only dealing with NUMA, but to me, PCI bus and NUMA are both kind of motherboard level constraints. Right?
Yeah,
go ahead.
Yeah, you're right that in principle, this could be like, because now the question is that do we want to kind of have this bottom up or top down in a way, but there's also the case where 2 devices, they don't have anything to do with each other. So there will never be a single byte going from device, let's say, foo to device bar. And if that's the case, then it really...
So if the plugin's the one doing this, he might just know that I would never communicate with this thing, so it can leave that branch out of the graph.
Yeah, so in a sense, the costs between these 2 devices is sort of like irrelevant, and the kind of the relevant cost is then the cost of the device to the CPU. Mm-hmm. If that makes any sense.
Yeah. So if you left this, I guess the way I'd put it is that if you left this this calculation done to the topology manager rather than the plugin, then you'd have a lot more branches in your tree because you couldn't rule out two devices that actually have nothing to do with each other just because they happen to be connected on the PCIe hierarchy
Yeah.
somewhere.
Yes, precisely.
Okay.
But this is
When
not-
you're traversing your algorithm, you actually you know which resources is going to be used by the pod. So, like if a resource is not going to be used, you can left out the edges of the graph, which is not relevant to this particular pod.
I see. Yeah, that's actually a bigger reason I can see why you would want it in the plugin, because he's already going to know, well, I'm actually only considering these 4 devices. So I can just do my cost of those 4 to the other things on the system. Yeah. Okay.
And then the case 4 that it's on the next slide. Now this is the interesting case when there are 2 like completely separate resources, but there is actually like an out-of-band connection between the devices. And on this picture here, the example is that the network interface card and the FPGA, they're both connected to this super fast network. And if they want to like communicate between each other, it's much faster to do it using this sort of off-band connection. Like instead of going through the whole system way through the PCI buses and so on. And it doesn't really matter what is the type of the off-band connection. It can just be like physical wire between 2 devices, 2 GPUs, like whatever, or it can be like a network connection or something else. But the fact remains that the only devices or the only components in the system which sort of understand this is again the device plugins. So if there is such a connection, then the device plugins need to somehow be aware of it. Somehow they need to be configured. The devices need to be configured to use it or something. So device plugins need them to communicate the lower cost. So this is again like a responsibility of the device plugins.
Apologies if you're going to cover this in a bit, but I don't see it in the CAP, and I'm wondering what is the end user experience? How would an end user request a particular topology, or would they basically say, give me an FPGA device that is closest to this other related device that I'm requesting? Or
My guess is that they're just requesting resources, and this does magic under the hood to make sure that they're closest.
That's right. That's the idea.
But it's not. You don't always want closest, right? Sometimes you want a complete isolation, and so I guess how is the user going to be able to influence that? I guess.
Yeah, that's an excellent question.
Sometimes you
So-
want affinity, sometimes you want anti-affinity in a way.
So I had a brief chat with Luis about this, that how to actually best like incorporate this to topology manager, and she was suggesting that this might be just a topology manager policy. So now when we have the current thinking that the pods themselves might be able to choose policies, then that might be one way to actually like use it. But if you don't want to have close devices, then you just select like some maximum graph cost policy or whatever. So that could be one way to handle it. But right now, sort of the default thinking is that it would make sense to choose. In, I guess, 99% of the cases, it would make sense to have devices which are close to each other in the same container.
Practical assumption is what if your pod requesting or if your container requests multiple resources to the same container, usually it means what those are going to be used together by the same application. So,
sure, I'm actually more referring to pod to pod resources. Sometimes you want pod A to get a device that is anti-affined to a device that is in pod that is used by pod B.
no, right now, what this algorithm is covering only the scenario what topology manager
within a single pod. Yeah,
within a single pod. So it's just exactly the same decision making what topology manager is doing right now.
sure. Okay, yeah, I was just curious. Thanks.
Then the last slide is is some thinking about the changes to device plugins. Now, this is something which I haven't tried out in practice at all. So this is just a thought experiment at this point. But it's clear that there needs to be some sort of interface to the device plugin so they can pass up this cost information. So one thinking that we had would be to extend this topology info message so that it could actually have a map of costs between the devices. And then the second option would be like in this Kevin's skep, there would be this method interface, which we could ask, and then it could return this map of the costs. So I'm not exactly sure that which one would be better, but it might be that this topology info is actually like more static compared to this using the method to actually ask for the costs. And it could be like a performance optimization to either way, actually. So this is something which needs to be like examined. Then the helper library for finding out the costs in how the device is actually connected to the system. And there is also already like something which is used within this device plugins collection, which could be used as a basis for this work. And then we can have this or implement this in somewhat backwards compatible way to actually use this NUMA affinity information, like as the cost information or some approximation of the cost information. That of course we will lose many of these more advanced use cases, but we will have like this that already device plugins will get somewhat good resource assignment using that. And that was the presentation. And I guess what I still want to add is that as you have heard, and this is something of a bit like forward-looking exercise. So this is also something which might be like, if you go and review the KEP, then all kind of these comments of course are welcome, but especially this, that is this like a direction where we want to go? Do we want to actually like handle this like topology on this level? And if we do, then is this sort of this added complexity which comes from this when we compare it to this current NUMA way of doing it, then is it like worth it? Is this the right abstraction level? So these are sort of the questions which I'm sort of the most interested in.
Yeah, so I have just a couple questions and feedback in general. The entire proposal, I've read your KEP a long time ago, and I wouldn't say I forgot a lot of it, but I did until you went back through it today. And I think, you presented it very well. It makes a lot of sense what you guys are proposing and, what your ideas are. The only concern I had back then, which I also have now, is having the plugins themselves generate these costs. It still feels odd to me to have the GPU plugin somehow be aware of the network card plugin, or not necessarily the plugin, but the fact that there's other network cards on the machine, and then calculate my costs to these other devices, and then have them doing that back to me in some, asymmetric way, which is what your first slide was showing with the costs.
Yeah.
It just doesn't feel like it will scale very well if I suddenly have to know about all the possible device types that I would need to calculate costs between on the system. Go ahead.
Kevin, the thing about this approach is what you don't need to report the cost if you don't expect interaction between the devices. Yeah. So if you have a device which knows what it can transfer the data between each other, so for example, like FPGA and SRIOV network card. So the plugin knows what this connection exists, and this connection can be used by the workload when it reports. If it doesn't have like GPU with FPGA, for example, if we don't have anything in common, we don't report it. So those part of the graph are not considered in the calculation. But where the cost is reported only for the scenarios when the user can do a data pipeline between the multiple devices and system resources.
Yeah, the only way I see this kind of working in a scalable fashion, I guess, is if we can build this library that Ismo was talking about, where, you know, different people can come in and contribute their logic to it to say, oh, I just add, you know, I have a plugin and I have this logic that I'm going to insert into the library so that everyone else can leverage this to figure out what their cost to me might be. And then kind of not necessarily force people to, but it highly encourage them to always use this library to do that calculation of the cost between you and, you know, basically if I'm the implementer of the GPU plugin, right? I can add a something to this library that says, here's how you can calculate your costs to me. I don't know what that would look like necessarily, but
yeah, wouldn't that like depend on the bus and, you know, like
yeah,
lots of different, you know, baseboard things.
So the current library, what we have, it's done for device plugins mapping back to the hardware resources. So practically, like we are getting the information about the PCI buses and when the CPUs, and out of this detailed information, we do a rough approximation which NUMA node it is. So this is something what a standard Linux kernel and like 99% of us have in our systems. This can be used as a basis for this cost information prototype. But when, if you're talking about like the specific devices, I don't see it as a part of like one of a common library because, for example, like NVIDIA NVLink. So it's, if
that's kind of separate.
Third-party device plugin is able to use the NVLink and discover it, when it probably will be linked with some NVIDIA libraries, not really with Kubernetes like the common library, right? So like,
yeah, I agree, but I mean, I also think that NVLink is a special case because you only really care about NVLink when you're looking at one GPU to another necessarily. You know,
yeah, but there are similar buses like that. Like there are InfiniBand, which might be having like Mellanox specific issues. It can be like RDMAs, again, vendor specific, and so on and so forth. So like for common hardware, we can provide the library which can detect. But if it will be some special out-of-band connectivity between devices, I think it's vendor responsibility to talk, like, or to provide the libraries how to detect them.
Yeah. Yeah, I guess I still can't wrap my head around how I would sit down and write my plugin based on this, right? In a generic way. You know, I'd somehow have to know about all the possible devices that I could ever connect to, and then write the way that I could calculate costs if they happen to be connected on the machine that I've now deployed the plugin on.
But you don't need to calculate it for all of the devices. So
sure, just the ones that I care about having affinity with. Yeah.
Yeah. So, for example, like you have multiple GPUs and you have NVLinks between those. You expose only information about your NVLinks between those devices.
Oh, and I want to potentially expose the costs to network cards that are closest to me because I want to make sure
so
those
when
kind
you
of
discover
like your
the network card and
your
you
case
say,
for
this one, this instance that close to this network card.
Yeah, I mean, I definitely see how it would work. It still doesn't quite sit well with me to think that the GPU plugin is discovering and calculating costs to other device types on the system. But I could be convinced. It just still doesn't quite feel right.
Yeah, I guess in the end, so the important thing is that we can get the distance to the overall system from each device, because then we can actually like get reasonable this NUMA affinity like out of box. But then whatever the devices they can then tell about the other devices and their costs to them, then that's like a bonus, and that can be like also like a long road. And it could be that whenever the sort of the devices get more complex and the interactions between them get more complex, then the device plugins are going to get more complex.
You have the basic affinities like NUMA and whatnot set up, and then only over time you could add these affinity cost calculations to your plugin when you knew. In fact, you could even do it on a one-off basis. You've got a very special purpose machine and you have some patch to the plugin that knows how to calculate the costs better on that. And at least then the plumbing's in place in the kubelet so that you can give it these costs so it can do the right thing.
Yeah, that's the idea.
Yeah.
We have exactly hardware similar to it, like the special card for 5G operators. So it includes like the FPGA, it includes 2 network cards, and it includes like some special ASIC for LTE, like radio encoding decoding part. So all of those, we know what it's connected together, and the user, when we get this pipeline, we need to get it together. But it's multiple different resources announced by multiple different device plugins.
Mhm. Yeah, I think framing it that way helps me come to terms with it a little bit more, that, you know, we put this machinery in place that allows you, the plugins, to kind of generate costs amongst any device on the system. You don't have to use it, but it's there. And if you choose to use it, sorry, if you don't choose to use it, then the algorithm will still be able to give you, you know, NUMA affinities, whatever internal affinities you would have calculated as if we had extended the topology manager that we have today. But at least now the machinery would be there if you do want to build some of this custom stuff into your plugin. What's built into the kubelet can actually handle that and give you the affinities that you're looking for.
Yeah, yeah, I think that's sort of the way forward maybe. But I think the first part is which I would the most want to see is that everybody like rush to the KEP and add comments and find issues there, and then especially think about the big picture, that is this sort of something which we would like to see? Is this something which we should like spend time on? I think that is the thing which is sort of like matters to me the most, because I think that this is the implementation details. They are something which we can like work out or figure out. But it's true what was said in the beginning, that the debugging will get like necessarily like more tricky, I believe, and complexity will be added. But then we will have maybe better performing systems.
Well, the one specific piece of feedback I'll give, independent of, you know, thinking that, not being comfortable with the fact that the plugins might have information about other devices on the system, is that right now there is no way to cover the case of specifically a GPU wanting affinity with a network card. And I know at least at NVIDIA, that's something that we really want to be able to do. And there's no easy way to extend what we have to make that possible. So there is at least one very concrete use case where something like this would you know, have a big benefit. So.
Okay, just in the interest of time, we've got about 9 minutes left. I think you know, we've gone through the slides in the KEP, and well, not the KEP, but the slides in the presentation. So what I got is just another request to folks that are interested to please review the KEP. And just a sort of general question: is this something that you know, folks in the community think would be useful and helpful? So if it's okay, how about we wrap this up, because there are a few more items on the agenda and we've got about 8 minutes. Everybody good with that?
Yes, hey, thank you everybody.
Yep, great presentation, Ismo. Thank you very much. Okay, so next on the agenda, we've gone over the second thing. So BG and Chris,
I think we can skip that one because it is not necessary to present this. It was regarding the discussion 2 weeks ago when we were talking about the 5G deployment and UPF on the edge, far edge, and etc. And if you guys want, I can present it maybe next week when we will have more time on maybe on Thursday. If you want, of course, because I don't think it's necessary right now. If decision will be tomorrow regarding the enhancement, and I see that Artyom has another point in the agenda, so maybe he can wrap up today his points.
okay, so we'll do that then. If you want, we can put it on the agenda for next week, and we'll move on to Artyom.
Okay.
Thank you, Chris. I had some proposal from our tuning team, like to disable load balancing of some CPU. For example, for all guaranteed pods with static CPU, we will have possibility to disable the load balancing. Like how you can to disable it, you just need to uh, disable some flag under the scheduler domains of the specific CPU. And I just wanted to know if it's a feasible solution to do it under the CPU manager, because again, for me, it looks like the most appropriate solution. So, for example, in case if you have some annotation that asking you to disable load balancing, and you have static CPU manager policy and it's guaranteed pod, so it will just, once it will allocate CPUs, it will also disable the CPU load balancing for the specific CPUs. And once you remove the container, it will restore the load balancing to the default values. I just want to know from the community perspective if it's feasible to add such functionality under the CPU manager. Thank you, guys.
Do you want it only for guaranteed CPUs, meaning ones that we would set up a CPU set for? Or do you want it for any CPU in the system that's given to any container?
Like we want it only for guaranteed pods, the same way as static policy for the CPU manager is working.
Oh, got it. Okay, yeah, sorry, I missed that when you said it. Yeah.
So practically, you're going to sysfs and the kernel interfaces and disable, or well, modifying the scheduler parameters for particular system.
Yeah, practically, I'm going under the proxy's kernel sketch domains CPU directory and just disable one flag. It's like bitwise end operation, and that's pretty all. And once I remove the container, I will bitwise to another set of bits and will restore the default flags. It's like the whole operation.
But that's actually architecture dependent and hardware dependent. So again, do we really want to have that architecture dependent components inside the kubelet? Because, well, kubelet is universal between the bare metal and the cloud nodes. That's one thing. Second thing, do I understand correctly what actually this, by doing that, you're actually trying to achieve like some real-time kind of scheduling for your workload? Because
yeah, exactly.
If you're doing real-time, when we have other problem which potentially needs to be solved in different ways. So like OCI spec, when the container starts, it can specify the real-time quota for the processes. And runC is able to put it into the scheduler parameters for the container. But again, this information is lost between the kubelet and OCI spec. So we might want to expose these real-time parameters up to the kubelet if you want for this particular case, instead of trying to kubelet directly go in and modify some kernel parameters.
Like, can you please edit under the document, like under the comment, because I still don't fully understand the connection between OCI and container. Like, if I understand, like OCI will inform you about the scheduling flags, right?
Well, what I'm saying is like we have architecture level where the kubelet represents the high level resources. It communicates it down to the CRI level, which like again abstract resources. When with CRI plugin like CRI or container, it doesn't really matter. It converts it to OCI parameters. And OCI runtime actually does the real tweaking of the kernel. So would it be like runC or any kind of like VM-based runtimes? Doesn't really matter. But like the component which interacts with the kernel interfaces is the level below. What I see in this proposal is like the high level thing will, like from one hand it does with CRI approach to container level, and on the other hand it goes directly and tweaks something in the kernel, which for me doesn't make sense. So like we have like two channels of communicating to the kernel for the same process. So if we really need to do it, then probably let's extend this stack between like CRI, OCI, and when OCI compliant runtimes to enforce those parameters if we need it. So that it become portable between runtimes.
Okay. So it sounds like
I think
Artyom.
he was trying to respond, but he was muted. I saw.
Oh,
Sorry,
sorry.
again. Sorry. So I need to pass the well information. Like I need to pass the request if I want to disable the load balancing to the OCI level, right? Do I understand it correct?
Yeah, I think that would be. I
OCI,
agree with that. Yeah.
and OCI using the like appropriate data message can enforce it using the kernel, or return error if it's not possible, for example, like on Windows container or something else. So like kubelet, at least in my opinion, it shouldn't be changing anything in kernel interfaces by itself.
Yeah, like even currently the way the CPU set is set on using the CPU manager, it doesn't set it directly. It passes it through the container runtime to the OCI spec, who then takes over from there.
Yeah, it can work for me.
I said that backwards, but you know what I mean.
It can work for me perfectly, but the question is if it's feasible, like to use annotation, and once the CPU manager will receive this information and pass it to the OCI level, like again, we probably will need to extend the interface or something like this.
Well, what you can easily do if you really need to do it is what you can create a small wrapper on top of runC, for example, and pass the annotation down. So practically all the pod annotations will be visible in the like runC level. And on create container request in runC, you can just parse those annotations and do the things. So for that, you don't like, if you want to use annotation, you don't need to change anything in the kubelet for that. You just like do the runC wrapper and that's it. Or you can define even like this runC wrapper as a separate runtime class and like also utilize different runtime classes for these parameters.
Yeah, that's it. It sounds like, I don't know, from my perspective, I agree with you, Alex, that it should be pushed all the way down to that level. But it also seems like, given his exact use case, maybe that effort involved to do that and kind of, push it all down there is the same as if he just implemented it as a plugin for his kind of one-off use case. So I think the bigger question is this something that would be useful in general to everyone? And is it then worth the effort to try and push it into the OCI spec and down from there, instead of just putting some one-off kind of annotation-based, I don't want to say hack, but hack in place, right?
Not a hack, it's modular design. And it's actually really easy to implement this kind of wrappers.
Okay, just a quick time check. It's 2 minutes past the hour, and I know probably several of us have another meeting to get to. So I think Artyom has got some different feedback, a couple of options to explore. Artyom, does that sound good for you to maybe take some of that?
I also will continue the discussion if you not versus it with Alex and Kevin.
I will add a comment to the document showing the example of this wrapper approach, so you can look at it.
Thank you.
Okay, there's one more item on the agenda, but let's push that. I think the request is there just to review this, so if folks could take a review, provide comments, that would be great.
Yeah, there's nothing blocking that other than the PR needed to merge. So, or the requisite PR had to merge. So yeah, we'll promote that.
Okay. All right, Derek, if you want to stop the recording, we'll wrap up.
One quick question. Do we want to have the next meeting this Thursday or it is next Thursday?
Great question.
I think it depends on how many agenda items we have, right? Is there anything in the backlog? You stopped sharing. I don't have it.
Oh, sorry, there was just one item. There's no backlog.
I think if tomorrow will be the decision about the enhancement, so maybe there would be questions what to do next with that, and what will be the next steps.
I don't know about this 5G things. If we want to do a presentation, I would be interested to listen to it.
Okay,
example.
Nice to hear.
We can do it on this Thursday.
Okay, so why don't we have the next meeting this coming Thursday for the 5G stuff?
All right.
Okay, and I'll send out an invite for that.
Yep.
All right. Derek, can you stop the recording? I don't think I can. And there we go.